Hello, during this session we're going to be talking about what is friction. So let's think about this. Friction describes a force which opposes motion. This is kind of what we've standardly accepted. Friction is something which always opposes motion, and we've considered some different types. We've identified things such as air resistance is a form of friction. So if there's a push on an object, friction will oppose the urge for it to move. So this means that this is important. Friction opposes motion, not just motion which is taking place, but potential motion as well. So this block on the right hand side could not be moving, and friction could still apply if there's an attempt for it to move. So let's look at this a little bit more closely. If we look at the figure below, both the blocks are made of the same material, but one is heavier than the other. So this is taken from How Stuff Works. Now, common sense makes us recognize that pushing the 400-pound block is going to be more difficult than pushing the 100-pound block. Now, the thing we recognize here is that the force of weight is actually acting downwards. So therefore, it shouldn't be opposing the motion of the object. This implies that there must be some relationship between the amount of friction and the downward force. Okay, so this is what we think about here. Now, we can work this out, that friction is the reason it's more difficult to push has to be explained at a microscopic level. So let's look at this at a microscopic level. At a microscopic level, we see that there's a whole range of ridges between both the surfaces, which may appear to be smooth to the naked eye, but at a microscopic level they're quite rough. And now if we set a block down on the table, the little peaks and valleys get squished together, and some of them may actually weld together. So therefore the weight of the heavier block causes it to squish together more, so it's harder to slide. And that's the reason why there's more friction apparent with the heavier object. Now there's a relationship here which we need to look at. So first of all, we're going to think about static friction. Static friction, this is a force that opposes motion from rest due to the contact between objects. Okay. So what it does, it provides an equal and opposite force to motion until a critical point when the force is overcome and it allows to move. Okay, so for instance, if I have a block on a slope, the static friction is what stops the block sliding down the slope. So let's look at this a little bit more closely. If we have static friction, and here we're thinking about the static friction of a bin. Okay. We recognize that this is formed due to the ridges between the two materials, the bin and the floor. Okay. Now what happens if I just try to push the bin slightly, then the static friction force will be equal and opposite to that. If I push it a little bit harder, then the static friction force will be a little harder than that. So what we find here is that the static friction force changes depending on how much force is placed on the object in the first place. All it's trying to do is keep it still. Now there's an approximate formula for static friction, and that means that the frictional force is equal to mu s, which is the coefficient of static friction, multiplied by the normal force. Okay. And the normal force is obviously equal and opposite to that of the weight in this situation. So what we have here is that we can work out what the frictional force is. Now, as there's the less than or equal to, just to show that this goes up to a certain limit. There's a certain limit. Let's look at a slippery slope, and again we'll think about static friction, so we'll try and break this down a little bit more. So there's some interesting points here. We know that the frictional force is going to be less than or equal to the value of the static friction coefficient multiplied by the normal force. Okay. Now, in this case, we can look at it in a little bit more detail. We need to recognize, first of all, that the frictional force is going to be equal to mg sine theta. Okay. So it has to be equal in size to the force which is being provided by the weight for the object to slide down the slope. Okay. At the same time, we also have to recognize that the normal force isn't equal to mg in this situation. The normal force is equal to mg cos theta because the block is at an angle, so the normal force is only equal to the component of the weight in the first place. If we break this down a little bit from these facts, we know that, so the frictional force equals mg sine theta, and the normal force is mg cos theta, so we can show that mg sine theta equals the coefficient of static friction multiplied by mg cos theta, which allows us to simplify and show that the coefficient of static friction is equal to tan theta. So this is a way of very quickly working out the coefficient of static friction in a situation. So that's some stationary situations. Okay. If I started pushing the bin, initially when it's not moving, we'll be thinking about static friction. But eventually I get to a point when I get it going, and there'd be a point where I have to overcome, and once I've overcome that point and it's in motion, then I have what's known as a kinetic friction, and this is the friction when motion is actually taking place. So when the object is sliding, this is the frictional force exerted on them. Now this can be approximately found as the frictional force for kinetic friction is going to equal the coefficient of kinetic friction multiplied by the normal force. So a similar rule to that of kinetic friction. Now, as you can see here, there's our coefficients of friction have been calculated for a number of different interactions between materials: steel and steel, aluminium and steel, copper and steel, rubber and concrete. Now the big thing to notice here is that in every situation the static friction coefficient is greater than the kinetic. Because if we think back to that previous slide, here we go, there's a maximum point which we must overcome to get it going, and once we've overcome that, then the coefficient drops down. And that's why we have the lower coefficient of static friction. So I'm going to give you a couple of examples now. Think about this problem and then do some calculations. Okay. A man is either pushing or pulling with a force of 200 newtons. The child sled combo has a mass of 30 kilograms and the coefficient of kinetic friction is 0.15. For each case, what is the frictional force opposing his efforts, and what is the acceleration of the child? Now here you've got to recognize that in first example we are going to have not just the weight of the child sled combo, but there's also going to be a component of the man pushing down, and that's going to have an impact on the normal force. In the second example B, again, what we're going to find is the normal force is going to be less, because this time the man has an upward component, and therefore the normal force is going to be less than the weight of the child sled combo. So with that thinking, put that into consideration, calculate the force for each of these situations, and then work out the acceleration. So in the first example, the frictional force is 59 newtons, and the acceleration is 3.8 meters per second. And in the second example, the force applied is 29.1 newtons and the acceleration is 4.8 meters per second squared. Okay, so hopefully you've done okay there. We'll go through another example. In this case, we have a block on a table and is attached to a block which can fall downwards and is linked by a pulley system. So we recognize that M1 is 10 kilograms and M2 is 5 kilograms. So with that in mind, you should be able to work out that the weight of M2 is going to be equal to the pulling force applied onto M1. So what value of the coefficient of static friction would stop the block from sliding? So that's the first question. Okay, so what would stop it from sliding? So thinking about this, you need to recognize the normal force, recognize the pulling force, and relate that to the static friction coefficient. If the box is sliding, so this is once it's begun sliding, and the coefficient of kinetic friction is 0.2, what is the acceleration? And finally, what is the tension of the rope? So we have static friction 0.5, acceleration 1.96, and the tension of the rope is 39.25 newtons. I have a third example, a third and final example. I have another static friction situation. What is the minimum static friction required to prevent a sledge from slipping down a hill of slope 30 degrees? So think about what we have here. Remember that the normal force is going to be equal to mg cos theta. The frictional force is going to be equal to mg sine theta. We know that the angle is 30 degrees. So what's the static friction? Take a moment to try and calculate this. And you should come up with a number of 0.577. Okay. If you haven't got any of those numbers in the examples, go back and review this carefully, because all we're doing is utilizing the formulas which we had earlier on in the presentation. So, final statement. Static versus kinetic friction. Static and kinetic friction are similar because the force is opposite to the direction of motion and proportional to the normal force. Coefficient of friction depends on the materials. However, static friction is an inequality up to a maximum. The coefficient of friction is typically greater for static friction of the same surface. For instance, wood on wood is 0.4 for static friction and 0.2 for kinetic friction. And hopefully that gives you an overview of friction.